So it does a pretty good job about it does a pretty good job on thermistors, and it does a pretty good job on piezoelectric. So usually when we use the term piezo, we're talking about something that senses some type of pressure. So piezoelectric, we talked about piezoelectric, right? It talks about Hall effect, does a pretty good job on that, and it jumps into ultrasonic. Then it gets into gas detectors and other things. But what we're going to do is we're going to go back and actually look at all the solid state sensors that I know of, and there's quite a few of them out there. So I think we went through with the photoelectric sensors, right? Everybody okay on those? Did we go through those? Huh? Through the beam, retroreflective, and diffused. Okay. And then we went over to manufacturing line. Let y'all look at some of these. Did we do that? Then, because I'm doing sensors in a couple of my classes, guys, and I'll get the two classes confused. This is a device called an optical interrupter, and we've got a couple of these on the line back there. We'll go back and look and make sure they are. Basically, all it is a through the beam. But what it is, it's in a self-contained unit. Okay. So when you look at this thing, you can look at it to the top. Usually it's labeled for you. So they got a polarity. This is the actual sensor right here. So that's actually what's inside the sensor. But you can't see it, right? You understand that. It's got a light emitting diode, and then it's got a photo transistor. And what advantage does a photo transistor have over a photodiode? We talked a little bit about that. Photo transistor. We're going to talk about transistors in detail. This is a photo transistor. Yeah. So when this thing comes around, you'll see one of them's got a little D on the top. This means this side would be the detector. Plus, it's transistor. They work the same. Yeah, but a photodiode, what we do on the photodiode is we put it into the circuit reverse biased. So what we have to do is we have to protect it with a resistor. And then we come over here and then we take our output either across the photodiode or across the resistor. And the problem we have with the photodiode is even though it responds real fast, it's dealing with leakage current, right? You understand? And leakage current is extremely small. So the problem we have with this is that when this guy sees light, we might come over here, might see like 10 millivolts come out. And we can't do much with that. So we'd have to come up and we would have to go through some type of electronic circuit that would give me gain anyway. A transistor is basically a current valve. And we have two types of transistors. So the actual main current path is up through the valve. And what do we do with water valves? We can control the flow of water. And you get a gain out of it. So if you ever turn your faucet on and try to stop that water with your hand, you're just going to end up with a big mess because you cannot stop that pressure with your hand. But with a valve that's got a screw on it, with the screw, because we get a mechanical advantage. So now I can take a faucet and do what? It don't take any pressure at all to control the flow of the water because I have a mechanical advantage. But what we do with a transistor is it's a current valve, and it works just like a water valve, except it's not controlling water, it's controlling the flow of current. So basically a transistor can operate like one of these guys right here. But on a rheostat, you're mechanically controlling that. So that's what a rheostat is, a current valve. But it's a lot like a water valve because you got a knob up there that you got to do what? That you turn to change its resistance. And what can you set the resistance at? Well, you can set it at 0 ohms, which means it will drop no voltage. Or you can set it at its maximum ohms and it would drop the maximum amount of voltage. And that's the same thing true with a transistor. But what with a transistor, the main current flow is up through here. But what I do is I control it with a very small current. So over here, I might be putting 1 milliamp over here, and over here, I might be getting 2 amps through my valve because we get an electrical advantage to a transistor. So what's nice about a transistor is we can get a lot more current flow through it than we can get out of a phototransistor. So it's just as fast, but we can get more current gain. We can get current gain out of it. Yeah, not a phototransistor over a photodiode. I might have said phototransistor by mistake, but a photodiode. Yeah, we can get a big current gain out of it. So now we can have kind of like a photovoltaic cell in there. It comes in, it generates a voltage on the tail end of the valve and opens it up. So now we can control this with light. So we can control the valve with light, which is what's so neat. And we don't have to add additional components. So when they figured out phototransistors, this basically dropped the need for photodiodes. You won't hardly ever see any photodiodes in new equipment. You'll see phototransistors. So I'm almost guarantee that guy's up there, that receiver up there does not have a photodiode in it. It's got a phototransistor because it's got to do things, right? So what I would have to do anyway is I would have to take the output of this little thing and I would have to run it through some type of amplifier anyway before I could actually use the voltage change out of a photodiode. So, but the problem is, LEDs, we put in there forward biased, right? And so anything above their VF is considered a short circuit. So we're going to have to come up with an external resistor between us and the voltage source. That makes sense? And then over here, what we would do is we'd take our output out here. And what we could do, we can make some things that we can't do with a rheostat is we can never make the rheostat act like an open switch. But with a phototransistor, we can make it act like a closed switch or make it act like an open switch. So if it sees no light, the transistor turns off completely, which causes this resistor here to drop no voltage. People think that resistors drop voltage, but resistors only drop voltage if they have watt flowing through them. Yeah, so VR is equal to what? Is I times R. So what happens is when we turn this transistor off, there's no current flow through here, which means this resistor drops no voltage. So that means technically we could get 5 volts out of there. And then, of course, when an object is not in the center, now the way that it's designed, the transistor acts like a closed switch, which means now it's a closed switch, which technically connects that to 0 volts, right? You understand? So we get 0 volts or no volts out of this thing, or 5 volts, excuse me. Now, what do we use these things for? Well, we use them for a lot of things. So all this is a through the beam detector. That's all it is. It's just that you have a transmitter on one side, and then you got a plus and a minus because you got to know how to bias these things, right? You understand that? So if you look at that one, when it comes around, one lead is labeled D, the other one's labeled E. So E would be the emitter, so that's going to be the guy that's emitting the light. D would be the detector, that would be over here, and then we would assign pins. So what they do, they don't actually show pins, is they'll come up here and put a little plus sign over there. So it means that's going to have to point back toward your positive supply. This makes sense so far? So if I was going to wire this circuit, if this is my D over here, my detector, then my positive, I would come over here and I would hook this to a resistor, and this would go back to my plus supply. And then I would take this, and my output would come right here. And then I would take this guy right here, and I would connect it to circuit common. And that's the way we'd wire these things up. Over here on my emitter, I would do what? I would take this pin, since this is plus, if this is plus up here, then this will be pin 4, and this down here would be pin 2. Then I would take this pin and do what? I would break it back to a resistor, and this would go to plus, and then I would take pin 2, and I would just hook it to common. And that's the way we would wire it. We'd actually wire this thing up. So this is my actually output would come off this pin right here. So this would be pin, this would be 1. And I'm just making these pins up, guys. We would have to look at it, right? You understand that? So how would we size this diode? I mean, we're going to have to add that external resistor. How would we size that? So we're just looking at this circuit right here. So here's plus, here's minus, and I got to come up with that resistor right there. How would I size that resistor? Here it's drawn as a resistor, but you're going to have to use resistor. How would I size that? So I need to know two things. I need to know what? R is equal to what? V over I. So what do I need to know, guys? I mean, this is just Ohm's law. I need to know how much voltage is going to drop, and I need to know a current value, right? What determines how much voltage is going to drop? What determines how much voltage this resistor is going to drop? It's in a series circuit. What determines how much voltage is going to drop? So if I came over and drew this circuit right here, guys, I came over here, I did two resistors. Now what I'm doing is I'm going to draw a resistor for the diode because I know it drops a voltage. And then I came over here and had a power supply right here. And I said, okay, guys, this guy right here drops 2 volts and it had a current of 1 milliamp. What size resistor would I need right there if I'm putting 5 volts over here? What size resistor? Well, first of all, I would say this guy right here is a series circuit. What's it going to drop? If I got 5 volts right here, this guy's dropping 2 volts. How much would that drop? It dropped 3 volts, and it's a series circuit, so I would say at what? 1 milliamp. I'm going to say 10 milliamps. Then I could size that resistor, right? You understand that? So what do I need to know? Well, I need to know the VF of the diode. If I know the VF of the diode, right, you understand, this is not silicone. I told y'all the average voltage drop of a LED. Do y'all remember that? Around 2 volts, yeah. Approximately 2 volts. If you got the data sheet, you would look it up, but 2 volts works for LEDs, approximately 2 volts. And normally we want about 10 milliamps to flow through them. So that means I want that resistor to drop 2 volts at around 10 milliamps. If it's a little above it, it's okay. If it's a little below it, it's okay. So what size resistor would I use up there? $200 ohms. So it's dropping 3 volts at 10 milliamps. No, we know the diode. All we're trying to do is calculate the resistor, right? You understand? And I knew it was wrong because I knew it was 3 on the top, and I knew the answer's got to have a 3 in it, right? What's that? Usually we use around 330. Yeah. Pretty standard. You see, sometimes they use 470s. 470s would allow less current to flow. So standard resistor to use for LEDs for regular LEDs is 330 ohms, and these are for the ones that run at 10 milliamps. Now, if you got these big high intensity LEDs, then by George, you need to look those suckers up, right? Because if you use a 330 ohm in there, it probably won't work. Now, what determines the size of this resistor right here? So we calculate the size of this one. What size would I use over here? Well, I know we're going to operate this transistor over here. We're going to operate it either as an open switch or a closed switch. So when we operate it at a closed switch, this guy right here is going to drop. If this guy, how much voltage would the resistor drop if I operate that at like a closed switch? So what we're doing is we're looking at it so it's acting like this. So how much voltage would the resistor have to drop? It dropped 5 volts. Okay. And then what we got to do is say, okay, we got to figure out how much current this guy right here could handle, right? So every solid state device is going to be rated at a current. So we'd look that up. Let's say it could handle 100 milliamps. Yeah, 5 volts, 100 milliamps. So about what would I use up there? Well, that's what you're going to do. So this guy here, you're going to have to look that thing up to see what current it can actually handle, right? Does that make sense? So once you figure out how much current that the transistor can actually handle, then that's what you would use to calculate that resistor right there. Everybody got that? Is that a standard size? We'd look it up, right? Because we'd have to use a standard size. I probably was going to grade them, and I got them out. They're supposed to be in the ready to be graded. I get so many interruptions here lately, guys. You're going to have to look out for me. Thank you, Brian. Well, what we do is we're going to have a blade or something that passes through this thing. So let's. Where's my optical interrupter at? These are very important. We have a capacitive sensor. These are capacitive sensors. We can simulate this guy on an oscilloscope. Yeah. So I'm going to switch this over to my camera. That's 60 cycles. So our scope wants to pick up 60 cycles all the time because that's Alabama Power, right, or TVA. And all I'm going to do, guys, is I'm going to come over here and just bring my hand up to this thing. And what do you notice? So what am I doing? So I have a capacitive effect. Usually I do this with the grounds, really cool. But I'm changing the dielectric. All I'm doing is doing what? So I'm changing the dielectric, right? You understand that? Does that make sense? It looks like it. Well, I actually touched the wire then, so I wasn't. This was actually me. So a lot of times, what we'll do, guys, to see if the scope probe is working, is we'll just come over. We'll turn the voltage down real low, and I'll come up here and just touch it with my finger. We do that to check the scope probe, and what's it picking up? It's picking up me, right? Because I'm a semiconductor, right? We're carbon-based life forms, so I'm picking up a voltage all the time. So this is what, but I'm not doing that. All I'm doing is coming up here and bringing my what? So I'm bringing my hand up against this, right? You understand? So I'm not touching the conductor anymore. So I'm seeing what we call the capacitive effect. So what I'm doing is I'm changing the opposition with the dielectric. This is me. This is actually me being not a good conductor. You'll see that? Thank goodness for this. Anybody ever use this, what we call the capacitive effect anymore? Y'all use that? Y'all have capacity? Y'all ever see a capacitive sensor? How in the world does this dang touchscreen work? It's a capacitive. All it is just thousands of capacitive sensors set up in what we call a metric. And when you come in here, you change the dielectric, and it's set up in what we call a metric. So the way your phone is set up, the screen is set up with thousands of lines going this way and thousands of lines going that way. And when you touch that screen, it knows exactly where your finger's at because it's reading those lines. This is capacitive sensors. This is what we're talking about right now. So how does it know you? It picks you up, right? You understand? When you come in here and touch this, you change the dielectric constant, right? You understand? And your phone picks that up. And that's why you don't have to apply pressure to these. Them HMI panels back though, those are resistive panels because they don't want them to accidentally be touched. So those back there, you have to put pressure on them. But these right here, these are capacitive sensors right here. What we're talking about right now. When you bring yours in, what are you doing? You're changing the dielectric constant, and it knows what? It knows where you're at on that screen. So this is a perfect example. These are capacitive touch screens. And what do you change when your finger comes in there? You change the dielectric. If you change the dielectric constant, then that output goes up, right? You understand? But it goes up on a row, several rows and several columns inside that matrix, and it knows exactly where your finger's on there. Well, you bring nothing in there, and it's set up so it's set up to sense certain things, and that's what we can do with a capacitive sensor, is we can tailor it to sense certain things, right? So that means if you got a glove on, right, you understand, and you put it on there, odds are it's not going to pick that up. Because this right here can't get through your glove. Oops, sorry. It's up here somewhere. So if I've got a glove on, I don't get this, right? You understand? So I could put a glove on, and I wouldn't see this, right? But you can buy special gloves that have special fingertips on them that allows that to go what? They're carbon impregnated in it, and then they let this go through. Huh? If they work on this, does that work when you put those on? Do they work? Can you work? Does your phone work? You really? Odds are you can tell because I have special tips out there on the very end. But you can buy them that actually allows them to work with a phone. You can buy gloves that do that. So I don't know if this would work. So no, it actually gets through this paper a little bit, but not near as much, right? So what we could do is we can actually set what we call a threshold on it, so we can block certain things and let certain things come through, right? So basically, capacitive sensors can be designed to sense. They can sense solids, they can sense liquids, they can sense a lot of things. They can sense gases if you let them actually get into the sensor. I need to watch out for me. So the shielded is what? It's more selective, right? You understand. And the unshielded is what? It's less selective through them. This guy, we don't have to worry about that. Then we have what we call inductive sensors. These are called, by the way, it's very confusing because in motor controls, they both call these things solid state limit switches. That's what they're called in motor controls. You have to know if it's capacitive. You have to know if it's inductive, right? You understand that? Inductive sensors, these are your metal detectors. Now, Hall effect sensors don't sense metal. Hall effect sensors sense a magnetic field. You know, so Hall effect sensors can't sense metals. Now we can combine it with a magnet, so we can actually have a sensor that has a magnet in there, and then the Hall effect is right here, and this would be the way you would buy it. And then when a metal surface comes across here, it would concentrate through the Hall effect, and it would appear to sense metals, but it's not sensing metals. It's sensing what? The magnetic field. You know? So Hall effects sense magnetic fields. These guys sense what? These guys sense metals. Have you ever encountered one of these? Probably every day. Every day. When you drive to work, if you go through a red light now, you sense an inductive sensor. That's that thing buried in the road out there that's sensing the metal in your car. That's an inductive sensor. So these guys sense metals. So these guys, when they're working, they control our lights, right? Most of our red lights now. Huh? Well, it depends. What we can do is on those loops is one thing we can do is we can set what we call the sensitivity on most of them. So like on 280, a lot of times if you're in that loop, those turnarounds, it will not ever change unless you have more than one car sitting there waiting. So what they're doing is sitting there looking for more metal, right? You understand? You ever notice that? So some of them we actually require more than one car to actually cause them to set. Oh yeah, my motorcycle, of course, I used to ride all the time. Is this sensor out here at the gate would not pick up my motorcycle, so so I would have to, if nobody was behind me, if a car was behind me, I had no problem. But if there was no car behind me, I'd literally put my kickstand down. I'd get off my bike over and hit the crosswalk to walk, and then it would change for me. But yeah, we can set the sensitivity on a lot of these sensors, which allows us to make it ignore some metals and not. And what's so neat, guys, is the amount of metals we can actually detect by the sensor itself what type of metal it is. So people buy metal detectors all the time, and they're going around sweeping across, and it'll tell them what size they're looking for and basically what metal it is. So, and now most of them display whether it's a coin or a bracelet or gold. It's pretty neat. So we can. These would be analog. These are not analog. These are usually digital. So these are metal detectors. These guys are used any place that makes metal devices. These are used. We down at Brosville. They make door frames. Well, they make the door frames and also the electronics that raises and lowers the windows. They do that at Brosville. And they make the seat frames. They don't put the cushions on the seat, but they make all the electronics that controls our seats now. And cars has got a lot of stuff that in the seats controls now. A lot of them has heated seats, right? You got the lumbar adjust on them, so you can change the setting. You can lower them and move them back and forth. So that's what they make at Brosville. That's what they make. They make seats, and they make not the seats. They make the frames for the seats, and they make the door frames with all the electronics that controls those windows now. which is a lot more than it used to be. So inductive, these are metal detectors. These have oscillators on them. They have to be powered. DC, sometimes AC, we can get by without that. So this is a formula, by the way. It's okay. So what happens is that the amount of L, which is the amount of inductance, so these things are rated in inductance because their opposition varies with frequency also. And we call the opposition X sub L, by the way, 2 pi FL. So on this is just opposite of the capacitor. So when this, as frequency goes up, X sub L would do what? Go up. If frequency goes down, X sub L goes down. No, that's a good point. Since capacitors and inductors varies their opposition with frequency, we can't rate these things in ohms. So we have to rate them in the ability to store a charge. Sorta. These guys are rated in what we call henries. And you can't use H because so this stands for henries. It's easy to see capacitors because C, capacitance, but H, we use those to rate the high side of transformers, so they don't use L to get H to get people confused. They're rated. So L is for henries. So we would buy inductors in henries. These guys can store a charge too, but they store it magnetically. But what we need to see is they vary their frequency. I mean, they vary their opposition with frequency. They don't produce any electrical work, which is pretty cool. In these guys, we call them ballast. So the problem with gases. So fluorescent lights create light with shooting electrons through a gas. The problem is, though, they have a resistance to them. And we start off, they have a pretty high resistance, so it takes a lot of voltage to get them started. But the problem is once the electrons start moving through the gas, the opposition drops way down. So what we want to do is we want to put something that drops a voltage, right? You understand? When these things, so when they start off, they try to draw very little current. When they actually light up, they would try to draw a lot of current, but it would just be wasted power. So the problem is, if I was to come over here and use a resistor on these fluorescent bulbs, it would these guys draw a little current. Let's say I put 120 volts over here. These guys draw almost no current at all. So that means I might get about maybe 118 volts over here. That would allow the fluorescent bulb to light up, right? You understand? That makes sense. And then when it starts dropping a lot of current, this guy over here might drop, it might drop 110 volts, and that might only put 10 volts across my fluorescent bulb. Now, what's the problem with a resistor? Well, a resistor is a resistor, and a resistor creates what? Power is equal to what? I square R. So what happens is your resistor up there is going to get kind of warm, and it's producing watts that you're not paying for. You want to pay for your lights. You don't want to pay for resistors. So what they do is instead of using a resistor, they use an inductor. So it might have 1,000 ohms at a rate. It might have 1,000 ohms at 120 hertz. But the problem is there's no current flow through it. It's in and out of it. So what happens is that when these guys try to draw more current, then these guys right here would drop more voltage, right? You understand? But they don't consume any current. So what happens now is you get the feature of a resistor, but these guys don't consume any power. So every one of these lights have a unit in there called a ballast. And that's all it is just a watt. Just an inductor. That's all it is. And what we do is we get a voltage drop without producing watts. You buy a small one for your house, and it's got that little thing in it. If you pulled it off, you broke it apart, it would have a resistor in there. But those little fluorescent bulbs pull so little current, right? You understand that it don't cause any problems. So y'all run into these inductors all over the place. So every place you got, of course, fluorescent bulbs are starting to go out of style too. You know what they're replacing them with, right? LEDs. Yeah. We had a company that was hiring our students, and that's what they did all day long. Yeah, they'd take the ballast out. They'd have to pull the ballast out because you don't need it anymore, right? You understand? And then modify the fixture to either replace the fixture completely and go to LEDs. But we still have a lot of fluorescent bulbs. So what happens is when you add metal into this, what you're doing is you're changing L. So these guys sense metals. They can sense any metal, but they do a lot better job with ferrous metals. Metals where magnetic fields go through real easy. They don't do a real good job on aluminum. So if we want to detect aluminum, we got to get it real close to the sensor. Okay. Okay. So let's pause out at. It was out in Wylam. At they made shingles for roofing. I forgot the name of the company, and their weigh bridge wasn't weighing right. And we opened that thing up, and the pit was full of water. So, this is why your scale's not working. Y'all know where it goes. Oh man, I don't know if they used to have a Jim Dandy plant over here off of, but they don't. We hadn't smelt it in a long time, so I don't know what they're doing. Yeah. When the weather's just right, you can smell that over here. Yeah. And I do visit that every once in a while. But that big old weigh bridge that you drive over when you come in there, I used to work on those things. Ultrasonics. So what do we use ultrasonics for? Measure distance, right? We use measure distance. So how does ultrasonics work? How does radar work? How does sonogram work? Sends a pulse out, right? And then does what? Measures how long it takes to receive it. So what would be the problem with ultrasonic sensors? What would they have problems with? What did you say? Sensing. What would have problem? What objects would they have problem? Maybe I need to reword my questions. What objects would they have problems sensing? Not a flat object because it could cause the what? Not to bounce straight back, right? Or the material. You know, we have planes now that almost have no radar reflection at all because it's the material that they came up with that actually absorbs it. So we could have some materials that absorbs the waves and don't allow them to reflect back as good, right? But over here we have no problem because we have nice solid objects and we're getting square surfaces. So we just work real well. We can use these things to sense distance. We can use it to change, check motion. Guys, when we go about an hour, what do y'all need to do? Sonic sensors can measure what? Distance, movement. Yeah. So anything that'll reflect. Same system. It's just at a higher frequency. It's called radar. Works off exactly the same principle. Shoots out a real high energy pulse, hits your car, and does what? Bounces back. They know the speed of the pulse, right? You understand? They can calculate your speed. Works exactly the same way. Sonar in ships. Except sonar has to be a real low frequency because high frequencies do not travel through water. So what that means is sonar works exactly the same way, but that you can literally hear a sonar pulse. And y'all watch movies, they call it pinging, So if they want to know the exact distance to most things now, they'll use sonar. But they don't like to use sonar that much in submarines. Why? Because as soon as you ping somebody, they hear your ping and they know what? They know you're there. So, you saw my battleship. But it's still available on submarines, even though they don't use it that much anymore. But anytime they want to know the exact distance to something, they use their sonar. Yeah, when they communicate underwater, they have to do it. They have to use what they call extremely low frequencies, ELF, and they have to trail an antenna out of the back of that submarine that's like 2 miles long to communicate underwater. So most of the time they'll float a buoy. They'll send a buoy up to the surface so they can communicate at high frequencies, but they can't communicate underwater if they extend that antenna. Because antennas have to be a certain length depending on the frequency. So the higher the frequency, the shorter the antenna can be. The longer the frequency, the lower the frequency, the longer the antennas have to be. So for reasons that, huh? What's that? No, they're not transmitting. No, those are not transmitting. Those are receivers. You know, there's a difference between transmitting and receiving. And we're getting off on a tangent. So when we transmit a frequency, it has what we call a wavelength. So that's the distance that actually travels between points. That would be like the waves coming off the beach. They're spaced out. Well, the distance between the peaks, we call that the wavelength. Transmitting antennas have to be in what we call quarter wavelengths. The perfect would be the exact wavelength. So what that means is the lower the frequency, the longer the wavelength. And for your transmitter to work right, for your antenna to work right, it's got to be in wavelength. Does that make sense? So it means the lower the frequency of a transmitter the antenna has to be longer. The shorter it has to be what is, So y'all remember CBs? Y'all remember those big old whips they used to put on the back of the car, 108 inches? Why did it have to be 108 inches? Because that was the wavelength for CBs. Now what they did was they put what they call a loading coil in them, which did nothing, and it made your transmitter think it was what? That loading coil. So that's why if you ever looked at the old antennas, it had a big old round thing at the bottom. That was what they call a loading coil. And what it did, it made, yeah, the big old, some guys would drive these big pickup trucks and they'd put tennis balls on them, because what would happen when they'd stop, the big old thing would come and bop the top of their truck. So they'd put tennis balls up there. So that's the old days, guys. So now what do? We just use cell phones all the time. But your antenna in your cell phone has to have a certain wavelength because you're transmitting, but it's a real high frequency, usually around 2.4 gigahertz. So we're up in the what? Gigahertz. So your antennas can be what? But they're still not efficient, and that's why we call them cell phones. Why do we call them cell phones? Because we have to have so many of these towers, because your antenna's not that efficient. It can't be that big, right? You understand? It can be loaded, but so we communicate in cells. So these are some ultrasonic sensors. We have what they call sonograms. Anybody ever a sonogram? They use these a lot on women that's expecting, right? And what can they see with those things? They can see the baby. I had to have one when I was because when I was laid up in the hospital for almost laid up 9 months, they were scared I was going to get blood clots. So what they did is they actually did sonograms of my bad leg to see if they had any blood clots in there. And they could tell exactly where it was at. It was pretty cool. This is what we have on one of our robots over there. This is basically what we have over there. And these guys, we can set them up to do a span, right? You understand a span. When we talk about span on a sensor, we're saying, okay, we can set a what? Yeah, we can set an upper limit, and then we can set a what? So that one is electronically calibrated. So what we do is we have a block over there that's got L on it, and what we would do is we would manually jog the motor out to the center, right? You understand? And then I think we take the calibration and we touch it to the minus polarity, and it tells it to establish that as the low one, and then we touch it on the plus, and it tells us to. Y'all did that in that class, didn't y'all? You've had troubleshooting, hadn't you, Austin, that 208 class? I thought you did. So we let y'all calibrate that thing in the 208 class. And now you know one of my bugs, right? So what's one of my bugs? I just loosened that screw. So we put bugs in the line, just like things that happen there. So somebody had to deliberately unscrew that thing, right? Pressure. So this is one thing we can sense with solid state devices is pressure. A lot of times, guys, on these sensors is we combine another sensor, so we have a sensing element. And then we'll combine the element with another sensor. And then what that will do is then we'll combine this into a unit. So there's a lot of things that we sense that we can't sense electrically, right? You understand? We got to sense mechanically, and then we have to take a mechanical and then convert it back over to an electrical. That makes sense? Okay. So one thing we have in pressure is that we have what we call a diaphragm. And so we'd put pressure in that thing, and it would cause the diaphragm to either expand or contract. And then what we could do is we could put like an optical interrupter up here. And then when the rod came through, it would what? It would give me a true or a false. But the actual sensing element is mechanical, right? You understand what I'm saying? So sensing pressure, we got, and you can actually see it on this guy. You can see where the actual, so what they did on this one is they used a limit switch. So the limit switch was actually mounted back here, and then the pressure would come in here. And then what happens when the pressure came in, it would push the diaphragm in, right? And this would come up and it would hit a limit switch, and it would tell us when we got to a certain pressure. Does that make sense? Or we could have done what? We could have put an optical sensor back here, had a blade, and then when it came back and pushed up and blocked like a through the beam and it blocked it, it would tell us it was at a certain pressure, right? Everybody understand that? So a lot of these sensors, some of these sensors, the actual sensing element itself, if I can find my camera, the actual sensing element itself is mechanical. And then we combine it with another sensing element to come up in what? And create an electrical sensor. So here's the diaphragm. This is what we call a bourdon tube. And this is used a lot. So what we do is we put pressure in right here, and it comes into this tube right here. You see the flat tube right here? And then what would that cause it to happen? Well, it causes this tube to try to straighten up. So if you ever been to a birthday party where they had those little things you blow into, right? They're in a what? They're in a curl. When you put pressure in it, what does it cause them to do? Roll out. That's a bourdon tube right there. Is it Bourden? Bourdon, if I'm saying that right. So our sensor, here's actually where the sensor would be. But this could be anything that just does what? It just measures this. So we could use a potentiometer. So when this thing moves, it actually turns the potentiometer. The potentiometer would give us a voltage that's proportional to pressure, right? You understand that? So here's Bourdon tube. And we got one more too, as soon as I can find it. We're making Kelvin get his exercise today. This is another pressure sensor. This is a bellows type. By the way, these things, we say they sense pressure, but they can also sense a vacuum. So right now, if I put a pressure in here, it would cause this thing to do extend. But if I came up here and put a vacuum in it, it would cause it to do contract. So even that guy right there, we could use it to measure not only a pressure, we could use them to also measure what? A vacuum. But this is going to have to be combined with something electronic, right? You understand that? Because this is a mechanical sensor. So somehow I would have to combine this with something by electronic. So I can make this thing turn a potentiometer when it goes in and out, right? You understand? Or if I want to do, if I want to specify a certain pressure, then I could actually have a optical sensor up here that it breaks the beam when it gets up to a certain pressure. I think this is the last one. I do, I think. And if you're in the sensor class, I have to apologize. You see, we're repeating a bunch of this stuff, right? In fact, I should have let Brian teach this. You want to teach this, Brian? Kevin? I don't see my pressure switch, by the way, guys. The one that's got the tube on it. Dang it. We ain't got there yet. It uses what we call a strain gauge. Strain gauge, yeah. Huh? Probably not, but you're close. You mean it turns your compressor on and off, or basically measures your pressure. Usually, the thing that measures, if it's got a dial indicator, then it's going to be using a Bourdon tube. So that's what the Bourdon tube does. It would automatically. You understand, Vondell? So a Bourdon tube. So if it's got a gauge on it. Oops, sorry. So if it's got a gauge right here, then what we could do is we could just literally take this guy here and attach it to a rack and pinion, and then that guy could actually be turning. That guy actually turns the dial on it for you. What they do on the ones, I've got one that's just got a rod that sticks up, and what these are is these basically have what we call a calibrated spring on them. So we know springs can either do what? They can either expand or contract, but they do it at a pretty precise pressure, right? You understand? So these guys that you buy, the tire gauge pressures that you buy that you just plug in and it's got the rod that shoots out the back, that usually has a spring on it, a calibrated spring, which basically contracts or expands with certain pressures. So, good question. But if it's got a dial indicator, if it's a pressure dial indicator, then it's probably got a what? It's probably got a Bourdon tube in there that actually has a. In fact, that one might have it. It's got what we call a rack and pinion. I don't know what a rack and pinion is. Have y'all heard the term before? Most cars have rack and pinions in them. Used to. This is basically you have one linear gear like this, which is a straight line gear, and then you have one circular gear that meshes with that. So rack and pinions either take a linear motion and convert them into a rotary motion, or takes a rotary motion and convert it into a linear motion. So your tires, your front wheels require linear motion, right? But your steering wheel does what? Rotates. So in the old days, you had a rack and pinion. If you looked, you had a big old box down there, and your steering wheel went into it. Now basically we turn with hydraulic pressure. So a tire gauge that you go out to and you measure your tire pressure for, would that be digital or would that be analog? It'd be analog, right? Well, analog sensors can be too. Very definitely. So you can go in if you got a HVA system and you got a thermostat, you measure the temperature. You're not measuring a temperature, you're measuring the temperature. If you put a little thermal gauge, put a little thermometer in your mouth, you're not measuring a temperature, you're measuring the temperature, right? You understand? If it was digital, it would either be true or false. So we could set if it was a digital thermometer you put in your mouth, we might have an indication if it was below 96.8 or above 96.8, but we wouldn't know how far below it was or how far above of it was, right? That's digital. Digital, it says, okay, it's either what? True or false. Now, sometimes we can set a span where it's true up above here and false, and y'all understand between a range, but digital is either what? It's either true or false. It does not tell you the value, it just says you've met a certain condition. Analog means these guys actually give you the quantity that represents what you're measuring. So I've got a tire gauge. So my wife's on her van, she's got an indicator that tells her the pressure in the tires. So you can actually go over there and it'll tell her her tire pressure inside the vehicle. We don't have to use a tire gauge on that thing. And why? Because it's analog, right? You understand it's got an analog sensor out there. If it was a digital sensor, all it would do is say, okay, if you wanted to run 35 psi, it would say, okay, you're above 35 psi, or you're below 35 psi. It wouldn't tell you what air pressure you had in there. It's either what? It's either good or bad, right? You understand that? So analog has the advantage is that it's going to give you a what? It's going to give you an output that is proportional to what it's trying to measure. Here it says pressure. I should have had this. So analog sensors are going to give you a voltage or a current that is proportional to what it's trying to measure. Everybody understand that? So we need analog sensors. Why do we need analog sensors? Huh? To measure things, right. So what type of sensor has this got in it? Is this analog or digital? Yeah, we call it a digital meter because it displays in digits, right? You understand? It's got an A to D converter in there, right? But this guy right here displays analog values, right? You understand that? So they actually sense an element that senses your voltage, it senses your current. These are analog devices. And then we take it and run it through an analog to digital converter to display digital information, right? You understand? So we called it a digital multimeter because it displays in digital. Used to, the analog meters had a dial on it that you used to do that. So can we get analog light sensors? Sure. Can we get analog current sensors? Sure. Can we get analog any sensor? Odds are you can. A lot of times we use a lot of digital in control systems, right? But what do they tell us? They tell us if something's there or something's not there, right? That makes sense. RFID. We had a guy in our night class. He has a Samsung phone that's taking the sensor class, and that phone would actually measure this RFID tag on those blocks back there, which is pretty neat. These use electromagnetic or electrostatic coupling in the RF frequency spectrum to automatically identify RFID tags attached to objects. Where do we run into these things all over the place now? Shopping, yeah, most department stores have them. They attach an RFID tag on their clothes and stuff like that. And then when you walk out, you go past the sensor, right? You understand? That trips if they don't take the RFID tag on it. Some of them they actually blow. little small ones. They'll run it across that thing a couple of times, and it literally blows a link inside there, a little fuse inside the RFID tag, and disables it. Those guys are really, really cheap. These are usually paper thin, right? You've seen those? And they have the big ones that they actually clamp onto your clothes that has the ink vial in there. That what happens when you try to take it off? It breaks the ink and, yeah, and stains your clothes. We do have what we call passive and tags and power tags through induction. So what do we need to induce a voltage magnetically, guys? That's what we're trying to make. What do we need? This will be on the next. Explain that to me. You're making an EMF. So these are the way all our generators work. Whether it's a DC generator or an AC generator, they use this feature. And what do we mean by relative motion? It's what you move. You can move the conductor through the magnetic field, or you can move the magnetic field across the conductor. So what we have in some of your RFID tags is we have a little secondary of a transformer, and then what you do when you go past that paddle, it generates a magnetic field which induces a voltage into it, which actually powers the RFID tag inside there. So a lot of your RFID tags are not powered; they are actually powered up by the sensors, right? You understand? So if it was powered, that means they would have to put a battery in there. If they put a battery in there, that means Walmart would have to go out to all these RFID tags every once in a while and change all the batteries. So those are actually powered by those paddles that's on the side that you walk through. These would be called the passive tags. Then we have power tags. These are usually, they could have a battery in them. They do have, some of them have batteries in them. And some of them are powered through induction. So most of them are powered through induction. So our RFID tags that we have on some of our blocks back here, these are powered through inductions. So this guy's phone actually it was a Samsung phone. I don't remember what it was. But he could actually read the RFID tags on our units back there. Or it looked like he could anyway. So these are actually electronic circuits. So we have an electronic circuit that they can store information in. So literally, you can store information in these some of these RFID things. So it's very popular now with animals for them to do what? To inject a little RFID tag into them, and it tells you basically how to get in contact with the people that animal belongs to. So if you got an animal that gets outside every once in a while and you can't afford to yeah, they actually inject it into their skin, usually back here in their neck. And then when they go to the vet can just do what? Scan it, yeah, and it tells them who the pet belongs to and how to get in contact with them. So, yeah, it is. They've been doing it for quite a while. They do it. A lot of ocean researchers do that. They'll attach these. Yeah, they'll tag these animals, and those are usually powered, by the way. So they yeah yeah. Wait till it grows up, right? Come back and find that fish. So we run into RFID tags all the time. All the time. You could. Yeah, Brian brought that up. I don't know where it's at, but but Jason Bourne had one of them. You remember him taking it out in the movie? Yeah. You haven't watched the Jason Bourne movies? Oh man. Huh? Yeah, he plays it. He does a real good job too. And he played in the what was the Martian, that movie? He did a good job in that too. He's a good actor. Jason Bourne, if you like, yeah. You watch the John Wick movies? Yeah, I'm waiting for it to come out on DVD. So if you like action movies, Jason Bourne, and John Wick. John Wick, he kills how many people in each movie? Somebody counted them somewhere. Temperature. I think we've already looked at thermistors, right? So we have these types. We have thermistors, which everybody okay there. We have two types. We have NTCs and NTCs and RTCs. No, I'm sorry, ETCs and PTCs. What does those stand for? I'm talking. Yeah, positive. So that means their resistance goes up with temperature. An NTC means their temperatures will go down with temperature, right? Everybody okay? The ones that we have are NTCs. Thermocouples, we're going to run into these a lot. What they found out a long time ago is that if we take two dissimilar metals and we bond them at a tip, what would happen is that when we expose that tip to temperature, these guys actually generate a difference in potential. That's proportional to the voltage. So these guys actually will measure temperature. They're really fairly accurate, produces a voltage that's proportional to temperature, uses a junction of dissimilar metals. The types are determined, the types of metals determines the temperature range. And we can be purchased to measure temperatures from anywhere from 0 to 4,200 degrees Fahrenheit. So out at US Steel, they would actually take a thermocouple and dip it into the steel to see how the melted steel to see how hot it was to verify that it was the right temperature. Because they had to make steel of different thicknesses. I mean, different temples. I mean, I'm trying to say it. Different strengths depending on how hot they got it, and then what material they mixed in with it to get different types of steels. Steel melts around 2,800 degrees. It did. They had a different story. You don't understand hot unless you've been around melted steel. You just don't know what hot is, believe me. So I worked at US Steel as an electronic repairman for about 4 years. It's hot. No, you didn't want to fall into that. You probably wouldn't feel anything. So where do we have thermocouples at, guys? In your house, where do you have thermocouples at? The thermostat that on your HVAC, these guys usually, I've never seen one use a thermocouple. They usually use thermistors. What's nice about thermocouples is they are linear, which means they give you a really accurate voltage that represents so what we use thermistors for, and we talked about this, we use a negative temperature coefficient, so these are nonlinear. And why we get by with thermocouples in our house, because they're a lot cheaper than, thermistors in our house, because they're extremely cheap. I mean, you can get these things for a song, but we only operate them over a very limited range. Y'all understand that? So a very limited range appears to be linear, even though it's a curve. If I'm going to cook a roast in my oven, by George, if I want 250 degrees, I want to cook it at 250 degrees. And we've got a wide range of temperatures, so your oven uses a what? It uses a thermocouple. It does not use a thermistor. It uses a thermocouple. Right. So usually in your refrigerator, you set your temperature on your refrigerator. It's supposed to be really accurate, right? You understand? So usually your refrigerator does not use a watt, does not use a thermistor. It usually uses a water thermocouple. So that's two places where you probably got thermocouples in your house. You have your stove, your oven. Yeah. Usually on your eyes, you don't have a temperature. You have a range, right? Those use a thermal metallic strip. So what a thermal strip or bimetallic strip? I'm sorry. So bimetallic strip, what they do is they combine two metals together, and they have what we call two different coefficients of expansion. So y'all know when metals heat, they do what? They expand, right? When metals cool down, they do what? Contract. And they have what we call different coefficients of expansion, which means they expand at different rates. So if we bond these together, these two different metals together in a strip, and this one expands faster than this one, then what it would do is it would make the strip do what? It would bend. So that's what's happening in your toaster. You got a bimetallic strip down there, and when you latch it down, it goes under the strip, right, and latches down. And then when it gets hot, what happens? It'll bend up, and it's got that spring on there, and it'll pop up. So bimetallic strip. So that's a good point, but yeah. So on those, you don't basically, and what you're doing is you're adjusting the tension on a spring. So when you go to hotter, you make the spring have more tension. So the bimetallic strip has got to go further, right? Does that make sense? To set the temperature, probably. It depends on what it is. If it's got electronic thermostat, then it's probably going to either be a thermocouple or the next guy that we're going to look at. It's called the RDT. What determines the resistance of a conductor? Well, not the coil, the resistance of a conductor. You're right. The more coils it would have, it would have more resistance, but that's not size, material, good, distance. No, you're on another thing. Brian said it. What did you say, Brian? Length. So that's what the coil does. You add more what? Length. And then what's the third thing? Fourth thing? The size of the conductor, the material it's made out of, the length, and what's the fourth thing? The tolerance is once we figure out a resistance, right? You're thinking resistors. So as metals are heated, their resistance goes up. If metals are, so that's why if you ever look at the ampacity chart inside NEC, they have different ampacities depending on what type of insulation you have on there. So this is why Alabama Power, if they don't have to put insulation on a conductor, they don't put insulation on a conductor, right? You understand? So these conductors that's up in the air, they don't insulate those. Where do they start insulating the conductors at? Yeah, when you can touch them, right? You understand that? So because insulation actually lowers the ampacity of a conductor because it keeps the temperature in, right? You understand? So if I have a certain conductor made out of a certain material at a certain length, then I can measure what with it? If I have a conductor that's a certain size, made of a certain material at a certain length, then what can I measure with it? I can measure temperature because what's going to change with the temperature now? Yeah. So, and these are what these guys call RDTs do. That's all there are. They just a long wire, a lot of wire wrapped around a ceramic thing. That's all an RDT is, and it measures temperature. These guys are very accurate. Do y'all know where y'all use these at? The resistance goes up. So if the heat goes up, the resistance goes up. Once you have a certain size conductor, once you have a certain length, right? You understand a certain material, then what determines the resistance? The temperature. So if temperature goes up, resistance of the wire goes up. If temperature goes down, resistance of the wire goes down. Where do we have these at our house? Well, it depends. Anybody got an electric water heater at their house? Yeah, mine's gas too. And it's got the rods that stick in the side. Those are RDTs. Those are so you can cut those things apart and you see nothing but what? Rope, yeah, coils of wire. Oh, I've got one up here. Could be. This is actually. So I had one of my units that went bad, and I got a bunch of parts off of it. This actually stuck in the firebox of my heater because I had a gas heater on my house, and this right here is an RDT. See it? I'll pass it around. It's just not a bunch of watt wires. Yeah, wire. This is a thermal strip, by the way. It got tore up right here, so this is a thermal switch. So this actually came out of the firebox on my heater. It's probably made of a wire that already has a resistance to it. So we use a lot of tungsten wire. A tungsten wire has a really good heat. You know, it's got a real high melting temperature. So tungsten wire is used a lot. Platinum wire is used a lot on high quality RDTs. It's just that platinum wire is very expensive, right? You understand? We could use copper wire. Yeah, we could use copper wire. I mean, we could use copper wire, and then we could do what? Just wire it, round it around something like ceramic, and then we could use that to measure heat. Now it's going to change resistance, so we'd have to somehow convert that into either a voltage or a current, but we've already looked at that, right? So RDTs are very popular. So the problem we have with thermocouples is they don't like real low temperatures. So they like high temperatures. So these guys are usually used for temperatures that's less than what? 600 degrees. These guys are very accurate. Must be externally powered. So the advantage of a thermocouple is it generates power, right? You understand? So no external power is required. RDT has to be externally powered. But normally we don't use these to measure real low temperatures. Normally to measure real low temperatures, like that's, we use, yeah, thermocouples actually generate power. They actually generate a voltage that's proportional to temperature. So if you've got a gas water heater, of course, a gas water heater, we have what we call a pilot light that burns all the time. And we want to know if that pilot light is lit before we turn on the main gas, right? Because if you set that temperature and there's nothing in there that senses when the pilot light is lit, then you're going to dump raw gas out into wherever your water heater's at. So how do we sense? And what we want to do is we want something that generates power so we can actually come over here and open up the main valve. So what do we use on gas water heaters? What has a temperature sensor that has the ability to generate power that can open up a main valve? Thermistors have to be powered. If you've got a gas water heater, there is no electrical power running to that. Well, I don't have that. That's a I have that too, but that's a piezoelectric. You don't have power line. You don't have power. You don't have electric wires running into your water heater, do you? And it's gas. Now go out there and look at it. It would make so that you go out there and look at it when you get up. Normally that's normally they use exactly the same thing that you use on a gas grill. Now that's a piezoelectric crystal. Yeah. And when you hit it, you hear it pop like that. Pop. Well, what it's doing, it's snapping a thing up against the piezoelectric crystal, which creates a spark. Yeah, those are actually those are actually you're actually rubbing a piece of metal. You can actually buy those where you can start campfires with them. You strike the two things together. Strike. That's what they're called, but it's works off of. Never mind. So what we have on most gas heaters. So what you need to do is go home and look at your gas heater probably and see if there's any power lines running to it. Yeah, but what you're using probably, if you hear that pop, then that's probably using that piezoelectric crystal in there that's creating that voltage, just like a gas grill. Normally these things have thermocouples in it. So the thermocouples do what? Create a voltage in which tells the main valve that it can open because the pilot light is lit. Yeah, that's the thermocouples. So what's nice about thermocouples, they create a voltage, right? You understand? It's just like it's kind of like our photovoltaic cell. They create a voltage from light. These guys create a voltage with what? With heat, right? You understand? And they're very accurate. The only big problem we have with thermocouples is that they don't like to work on very low temperatures. So normally when we get to very low temperatures, we'll move over to RDTs because these guys, they don't create a voltage, they vary their resistance, right? You understand? But we've already know how we could convert a resistance into a voltage, right? Okay, we looked at that. So I'm not saying it's your gas water heater doesn't have a power going to it, but it'd be the first one I've seen. Of course, I told that guy last night, Alexander. I told him that he couldn't read that RFDI tag with his phone, and guess what? He did. So so Rich is wrong every once in a while, guys. Infrared, y'all seen these guys, right? Infrared. What is infrared? What does the infrared sensors do? So anything that gives off heat generates a wavelength of light, right? We call it infrared, which means we can't see it, right? And they can measure the amount of infrared that comes off of it, and then they can determine the heat from that. The problem is, guys, these guys are electronic devices. They are totally electronic. They're not passive. They've got to be powered up. But you can get one of these at Harbor Freight too, by the way. So used to when they check the temperature on coming out of these vents, they'd have to get that big old a long ladder, and they put a temperature gauge that looks like looks just like a meat thermometer that people put in the meat to see if it's the right temperature. But all they do now is they have a little laser. It's not the laser that's doing the measurement. It's a little laser pointer, so they align it up correctly. Because you got to line those things up precisely, right? If anybody seen an handheld infrared temperature checker, it's got a little laser beam on it, so they can line it up, right? Because they got to be, they got to be pretty precise. So now these guys will come in. They'll come in on these guys, and they don't even get off the floor. They'll take their little infrared pointer, they'll point it up to that vent, and they can measure the temperature coming out without getting that ladder. Yeah, boy, they could just the maintenance they don't they just do what? They just point that thing at them, and they can measure the temperature. So it's really cool. But these guys are really electronic circuits. They're totally electronic. So they're made up a lot of stuff, right? You understand that? Anybody got infrared detectors at their house? Anybody got any lights that's got motion detectors on them? That's what they are. That's just an infrared detector. And that's what they're doing. They're looking for something infrared above a threshold, right? You understand? To walk through that, and it's picking. We call them motion detectors, but in actuality, they're just picking up you. Really? I didn't know that. A lot of times that light is kind of misleading. I don't know if they changed that or not. It was using a mercury vapor bulb, and sometimes those things get out of whack. You've seen street lights do that, where you'll turn on, and after a little while they automatically turn off and turn on and turn off because they've lost some of their gas. Uh, so that thing did it for a while, and you probably just interpreted it. So I don't think it's got a motion detector on. I thought they had that fixed, but like I said. So in electrical controls, and these are guys, we're going to have to show y'all these because this is symbols is the name of the game, right? And why do we need to learn symbols? Right, but why do we use symbols? I mean, we do that a lot now. We take pictures of everything. Well, and another thing, symbols is going to occupy a lot less space, right? And they're going to be a lot less cluttered. But the biggest disadvantage is that you got to know the what. You got to know the symbols. So this one, you go out and you buy a new DVD player. They don't give you a schematic. They give you what we call a pictorial drawing, right? What do they do there? And how big are those things? Well, they dumb you down because people don't understand symbols, but they understand what a TV looks like, and they understand what this looks like, and you don't understand that. So one way we can represent drawings is to do what we call a pictorial diagram, which means you actually do what? So I would draw a picture of that. So that was what I was doing a while ago, right? You understand? I had a picture of that. I had a picture of that optical interrupter, right? You understand? And I was literally making my connections to that. But instead of actually drawing the symbol for a resistor, I would come up here and actually do what? I would draw the resistor, right? I would come over here and do that, and then I might come over here and put the color codes on there. And so that's the difference. So what a pictorial drawing is, it makes you understand the operation of a circuit, but it occupies a lot less space. And it's a lot easier. It's not easier to understand because a pictorial drawing is a lot easier to understand because you're actually seeing what? You're actually seeing pictures of it. But if you understand the symbols, then it makes it a lot more what? Compact. So these are the symbols, guys, that you're going to have to know. So we have in motor controls. What time is it? Oh, okay. I saw Kelvin packing up. That's in electrical controls. This is the symbol of a sensor. A digital sensor. What's the problem? Is it sensing temperature? Is it sensing space? Is it a proximity sensor? We don't know. So they use one symbol, right? And that's the symbol in motor controls. They use that. If it's what we call a powered sensor, so this would right here right now. This would be our load. If it's a powered sensor, then what we would have to do is it would be what we call a 3-wire sensor. And so this is the way we would work that. What they did when they started coming out with programmable controllers is they wanted to come out with more detailed sensors. So the symbol of the sensor would tell you what it is. So these are ISO, international standards for sensors. So in motor controls, this is what we'd use for proximity switches, right? You understand. over here on PLCs, we actually use a symbol that indicates what the sensor is. So if you see this little old trough like that, this means it's a magnetic sensor. If you see this solid block right here, this means this is a metal detector or an inductive sensor. I don't know why I'm writing them there. It's on the other side. If we see this symbol right here, it means it's what? Inside the diagram. So what we do on here is we start off with a square, then we put this little diamond shape in the top of it. And this indicates that it's a sensor. Then we put the symbol down below that. So this is supposed to be black. So if I saw this with the two leads, that would identify it as a what? An inductive sensor. You'll follow me so far? And then we'll put one contact. And I don't have room, but you can see it here. I wish I could make this bigger. There's the contact right there. So now we know this is a sensor. I know it's an inductive sensor. And I know it's a 3-wire sensor because it's got 3 wires coming out of it. Now, these guys, currently what we do is we use colors that tells us where these things go. Now, normally it don't make any difference in AC because AC does not have a polarity. Everybody understand that? DC, it becomes very important on which lead you hook to the plus and which lead you hook to a minus on a sensor that has to be powered. So the color code, anybody had it? What is the one for plus? For the plus lead that goes to power as a sensor? Brown. Good guess. So this is plus. Then number 3, the 3 lead, this would be this color, this is going to be blue. And this is going to connect to your minus. And the actual output of the sensor is going to be black. And that gets us confused because usually when we see black, we think minus because we've been dealing with that for a long time. Now, 2-wire sensor. So this right here, do we see this is a 2-wire sensor? Then this is going to be brown. This is still going to go to plus. And then your actual output is going to be blue, which gets people confused because on your other sensor, it goes to power, right? You understand? So this is a magnetic sensor. This is a 3-wire sensor, so this is going to be a Hall effect. This is magnetic. Can y'all see what I'm talking about? This is a 2-wire sensor, so this is going to be a reed switch. So that's how you tell the difference. So a reed switch is going to be a what? 2-wire sensor. Hall effect will be a what? 3-wire. This one, if you can see it, this is the symbol. If you see that symbol, it means it's what? Ultrasonic. And these are the symbols for what we call a normally open contact, and this is the symbol for normally closed, which is different than what you'll learn in motor controls. The only thing I don't have up here, guys, I need to look that up, is the one we went over. What? I'll have to look that up, and that would be a temperature sensor. So I'll look that up and add that to my. Everybody okay? So what I'm going to do is I'm going to bring up some schematics or diagrams of this manufacturing line. And we have these diagrams on both the Festo line and the Amatro line. So we'll look at the first station on the left. And I think it's this guy right here. It's not this. One of them lists where each one of these things are connected to. One of them's actually the drawing. Okay, so this is actually the drawing. So this is our programmable controller. So basically on a control, what makes up a control system? Then we talk about that. Yeah, control system. I can't do real good with this one. This guy doesn't have. We have inputs. Then we run this into a controller. And then sooner or later, we're going to generate a what? Output, yeah. Sometimes. So we have what we call an open loop system. An open loop system means you don't have sensors. You tell the device to do something and you take for granted it's done. We have what we call a closed loop system, which we would take the output and then we would monitor the output with a sensor. And then this would feed back into the control logic. This is what we call a closed loop system. That signal, we call it feedback. So when we have a closed loop system, we tell our outputs to do something, and then we do what? Then we verify that it's done. So first of all, we generate an input. We said, okay, I want you to do something. Then our controller says, okay, what do you want to do? I'm going to do it, right? You understand? Sends this to your outputs. Your output says, do it. And then the sensor says what? If we're in a closed loop system, it would say it's done. And by the way, these are also called servo systems. And this loop right here is called feedback. So people have called it a feedback loop. So what does these closed loop systems do for us? We tell the system to do something. The controller takes that input, says, okay, do it, right? You understand? And then the sensor tells it when it's what? When it's done. Now, what advantage does open loop systems have over closed loop systems? Yeah, a lot cheaper. So if I can get by with an open loop system, I'm going to do it with an open loop system. Cheaper, because we don't have to add what? We don't have to add sensors, and then we don't have to have the electronics inside my control that handles the sensors, right? Does that make sense? What advantage does feedback have? Yeah, the accuracy. Well, we know that it's done, right? You understand that? So this is the inputs right here coming into my PLC. Then what happens? This right here would be the inputs. This is going to be the control, and this is going to be controlled by a program. So guys, I highly recommend you to take as many PLC classes as you can, because these are dominating controls now. Used to we had what we call relay logic, where all the decision making was done with relays. All that decision making now has been replaced by a computer. We call it a PLC. Yeah. And so if you get into any new installation, you're going to have to deal with PLCs. So if you're going to be in this field, I highly recommend that you get as many PLC classes as you possibly can. I can't get my draw to go off. So I can't move my display. There we go. So this is not good. These just have push buttons. So let's go down to the other one. So what type of sensor is this? So this is a 3-wire sensor, which means it's powered, right? So notice this lead of the sensor goes down to our plus block. So this is all plus, right? And then 3, here's 3, which is our other power lead. This goes down to minus. And then this right here is our sensor lead. This is black, by the way. I should have drawn that different. And this goes down to our PLC. I know it's a magnetic sensor. Why do I know it's magnetic? Got the little magnetic sensor. So I know it could either be a reed switch or it could be a Hall effect. Which one is this one? Hall effect. Why? 3-wire, thank you. So Hall effects have to be powered. Reed switches don't. So notice here's a magnetic sensor. This only has 2 wires, right? So I should have done these the right color. So it's got a brown wire that runs right here. This goes back to plus. So I should have brought this brown a while ago, guys. And since it's a 2-wire sensor, then the blue goes to the PLC. So this is reed, and then this is Hall effect. I tried to draw it. Are you okay? Make sense? 2-wire. Yeah. So what's this? I don't think that was on the symbols. Y'all should be able to figure it out. I know it's got to be powered, right? So this is a brown wire. Goes to plus, right? Here's my blue wire. Goes to minus. And then this right here would be my black wire. So just looking at that symbol, guys, and I can blow that up. Sorry. Good guess, but this might mess up my colors, but I can blow it up so y'all can see it better. What's this a symbol for? But it's got arrows pointing out of it. It's an LED. This is a symbol for a photo transistor, so this is one of our photoelectric sensors. No, the switch just shows us that we got one normally open contact inside here. So this is a what type of sensor? Just looking at it. Photoelectric, right? Yeah. Oops. Just don't want to draw. Got to go real slow. What time is it? Almost done. Let's see if we can find any more. So where do we have? Okay, what's 4B1? That's to read. 4B2, read. 1B1, 1B2. Listen. No, that symbol, that thing in the triangle indicates that it is a proximity sensor. That's all. That triangle, that's all it is. That means every one of these things has that symbol, no matter what. This is what indicates what type of sensor it is right there. Yeah. It just indicates it's a sensor, yeah. B3 would be a capacitive. Yeah. This is capacitive. This is magnetic, Hall effect. This is magnetic, it's Hall effect. I'm sorry. This is magnetic read. I was just making sure y'all was paying attention. Yeah. This is photoelectric. This is inductive. And that's another capacitive sensor. B5 is just some type of sensor. We don't know. Says it's a stepping motor ready. All we know is it's some sensor in there that tells us when the stepping motor's ready. That's a really good question. Capacitive. So I'm gonna make sure that these are up on Blackboard, because these are gonna be on the next test, guys. I don't know. I know y'all's comes once a month, so I think ours comes toward the end of the month, right? It's up on the calendar. So that's it for sensors. Y'all got any questions? So I think I'll make sure that this is in the handout section, and I need to find the symbol for which one that's not up here. Starts with a T. Temperature. Yeah. So where y'all gonna find these at so y'all can start looking at them? In the handout, not in the lab book, in the handout section. So, and what we'll do, guys, is we'll do a lab. Oh wait, I don't know. Some of y'all do that twice on potentiometers. Anyway, all right, that's all we're gonna do today, guys.